Susana Lopes. I am a junior researcher at the Center of Biological Engineering in Braga, Portugal, and I'm here today to present my poster, which is entitled Development of Next Generation Polymyxins Targeting Problematic Gram-Negative Biofilm Infections. So, as many of you know, antimicrobial resistance is one of the biggest health threats today of the 21st century, which is a big concern because it complicates many of the human infections, rendering them ineffective. So, because of the rising antimicrobial resistance, polymyxins have been revived, namely polymyxin B and E, have been revived as last resort drugs against complicated gram-negative bacterial infections, which are often multi-drug resistant and which are often associated with biofilms. So during the last few years, we have been witnessing an increased resistance to polymyxins, which along its toxicity results in a lack of effective therapies to treat these infections. So alpha-alpha dealkylysins, or DAGs, are a natural amino acids that possess unique characteristics such as bioactivity, metabolic resistance, hydrophobicity, and stability, which make them innovative building blocks in polymyxin analog design. So the main goal of our study was to design 6 new polymyxin analogs incorporating DAGs in their structures, and also to evaluate the activity of our new analogs against gram-negative and gram-positive bacteria, including in biofilms. And finally, to investigate the synergy with common antibiotics commonly used in these infections. To synthesize our analogs, we use a microwave-assisted solid-phase peptide synthesis, which allows it to assemble 2 specific DAGs, the dibenzylglycine and the diisobutylglycine, into the structures of the native polymyxins. And for this, we selected 2 positions of the native structure to incorporate the DAGs, so generating 6 new analogs, 3 for polymyxin B and 3 for the polymyxin E native sequence. So then we performed the activity studies of our new analogs by evaluating their antibacterial activity against planktonic cultures of Pseudomonas aeruginosa, 1 gram-negative strain, and against 2 strains of Staph aureus, 1 reference strain, Staph aureus, and 1 clinical isolate of MRSA. Then we performed the antibiofilm assays by challenging Pseudomonas aeruginosa biofilms with our new analogs, and then we evaluate their activity counting the CFU of the biofilm. So finally, we perform our combinatorial assays by combining our new analogs with taubromycin and ciprofloxacin, 2 antibiotics, and to predict the synergy between the compounds, we performed the checkerboard assays, and then we evaluated the best combinations against Pseudomonas aeruginosa biofilms. So, regarding the results, we can see that for the antibacterial activity of our new compounds, we observed that 2 of the 6 analogs showed the best effect in Pseudomonas aeruginosa planktonic cultures. These were B1 and E1 analogs, which both comprised the dibenzylglycine, a DAG, in the position 7 of the native structure of the polymyxin. And the MICs and the MBCs of these new analogs were very close to that ones of the polymyxin B and polymyxin E native sequences. Then we performed the antibacterial activity in Staph strains, and in the same case, the analog B1 showed to have an improved polymyxin activity in both Staph and both MRSA strains. In turn, the E2 analog showed also an improved polymyxin activity as the B1 analog. So this is very promising because the native polymyxins are not longer effective against gram-positive infections, and our analogs had a considerable effect in these gram-positive bacteria. Then we moved to our anti-biofilm studies by challenging the Pseudomonas aeruginosa biofilms with our new analogs. And for that, we selected the best analogs that showed the lowest mix in Pseudomonas aeruginosa planktonic cultures. And we observed that the polymyxin B1 analog showed the best result against Pseudomonas aeruginosa biofilms with log reductions very close to the native polymyxin B. This is promising because considering the purity of the analog, we estimate a better outcome for this new analog. And finally, regarding the combinatorial activity of our new analogs, we combined the analogs with tobramycin and ciprofloxacin, and we can observe that the polymyxin B1, B2, and B3 analogs and the polymyxin E2 and E3 analogs showed additive or even synergic outcomes when combined with tobramycin or ciprofloxacin. So then we evaluate the best combinations obtained in the checkerboard assays against Pseudomonas aeruginosa biofilms, and we noticed that the combinations involving the polymyxin E2 analog with either ciprofloxacin or tobramycin showed the best log reductions in Pseudomonas aeruginosa biofilms, ranging about 2.8 and 4.8 log. As main conclusions, we synthesized successfully 6 new polymyxin analogs, 5 of each having promising antimicrobial and antibiofilm activity, also in biofilms and also in combination scenarios with common antibiotics. And finally, and also importantly, DAGs are suitable for polymyxin analog design. So I would like to finalize my presentation by acknowledging to the funding of this work to FCT, the Foundation for Science and Technology here in Portugal. And of course, to all of you for listening to my presentation and for visit my poster.